sometimes even days to complete a certain operation. And so what are the kind of disadvantages? What might be the disadvantages of this architecture, right, for the modern world? First of all, when we talk about both ODS, operational data storage, and your enterprise data warehouse, you might face some scalability or performance issues. And there are two ways to address those issues. You can scale up to more advanced hardware, or you can scale horizontally, right, by migrating to some distributed systems, distributed storages. That's kind of speed and scalability concern. Also, what's pertaining to Hadoop, that's about real-time analytics. A lot of analytics is being done in Hadoop right now. And for some of the business operations, now you'd like to act more quickly. You would like to get information about your customers, about your operations, not in hours after ETLing data or minutes, as fast as possible. And some of the operations, for some of the operations, you might have some strict SLAs. And those are actually the challenges. So those are the challenges we see when the customer, let's say, comes to us and asks us, let's say, to help to accelerate, let's say, an operational data storage, or to accelerate somehow Hadoop or enterprise data warehouse. And I'll be honest with you, right? So Ignite is perfectly well designed for operational data storage acceleration. So yes, we can be deployed, for those of you who are not familiar with Ignite, we can be deployed on top of your existing database, like relational database, that could be Postgres, MySQL, Oracle, or it can be NoSQL database. We will store your entire data set in RAM across a cluster of your machines, and that's how actually you simply can gain performance benefits. That's actually our sweet spot, right? That's our bread and butter, how we accelerate existing deployments. In addition to that, that's not like the final destination in your journey with Ignite. As this picture shows, you can even go ahead and remove your, at some point in time, you can remove your existing legacy database from this architecture after you enable Ignite persistence. Once you enable Ignite persistence layer, you will get your data distributed across a cluster of machines, both in RAM and disk. And this like perfectly well fits the concept of for our relational, for our operational workloads. You're gaining performance speed and scalability for your reads and writes. That's simple. When it comes to analytics, right? When it comes to Hadoop in particular, the situation is not that simple, right? So it would be we are not replacing Hadoop entirely, and we are not designed for this. Hadoop is doing his job great when you use it properly, and the same is true for Ignite. So what we see is happening with Hadoop, we can take and offload some of the workloads which are running on top of Hadoop nowadays. And especially we are talking about those workloads for which you need real-time analytics, real-time performance, not the entire data set. And technically that's how we envision this on this slide. You take part of your existing data warehouse solution, you store your data in Ignite, and then you switch to Apache Ignite APIs. And so in return, what you're getting real-time analytics. You can scale when you work with Ignite, you're not required to store data in RAM only. You can use disk layer, which is kind of one of the most prominent requirements, especially for analytical workloads. You don't want to waste a lot of RAM for our historical data. We prefer to use disk layers. And like when you have this architecture, we would see throughout the use cases I've prepared so far that for some of the use cases you even don't need to have any ETL. If those data sets which you would like to store in Ignite, you don't need to replicate them back to Hadoop or vice versa. So like that's like actually a problem, right? So what might be wrong with Hadoop for certain business use cases, and basically how Ignite can fit that architecture. So now let's explore some of their real-world use cases. So how Ignite was used and is being used in production for Hadoop acceleration. So the first one, the simplest use case and the most straightforward use case is just you have your enterprise data warehouse separated from your HTAP storage. And And throughout this talk, when we talk about EDW, we are talking about Hadoop, and Ignite would be used as a HTAP storage. So, and this use case is pretty straightforward. Here is we have our existing Hadoop deployment, and we decided that we need to accelerate specific business operations. The simplest approach, right, which exists, you just take those operations and you switch those operations to Apache Ignite APIs. Apache Ignite supports MapReduce like computation, it supports SQL, it supports machine learning, a broad set of different capabilities. And usually it's not a big deal for Hadoop users to switch to Apache Ignite. So there is, I haven't met any kind of lack of any kind of functional gap, which was the reason why you cannot switch from Hadoop to Ignite. And then, like for those operations, you just extract a subset of the data which is required for those business operations. You store this data in Apache Ignite. And the only one thing you do is initially you need to preload this data from Hadoop to Ignite, and you do this once. And we have use cases for such use cases which run in production. So after that, the data, a subset of the data is in Ignite. You can remove this. Some of the customers, after that, once this subset is preloaded from Hadoop to Ignite, some of the customers even remove it from Hadoop because they don't want to use the data set in Hadoop any longer. The only one copy of this data set will exist in Ignite after that, and you just need to complete the preloading. When it comes to Ignite memory configuration, the memory configuration is pretty flexible, right? In Hadoop world, we know that on the disk layer is available to us, which is perfect, kind of, which is reasonable. In Ignite, you can use RAM and disk, and you decide how you would like to distribute your disk and memory space. So, for instance, the standard pattern which we are observing is the following. So, if you are dealing with some operational data set and you'd like to use Ignite analytics together with transactional workloads, then you will usually use RAM for your just kind of operational data, something that is hard, right? Something that you need to access all the time, so pretty frequently. When it comes to historical data which you take from Hadoop, just put it on disk, right? And dedicate this RAM. So you don't need to dedicate a lot of RAM for that data set. You can allocate it entirely on disk space. And what's like, how should you kind of base your decision, like what should you choose between Ignite or Hadoop? So basically, kind of my personal benchmark is when we're talking to the customer and they're saying, right guys, I'm just asking, what do you need from Ignite? Like, and if a customer asks, we have some analytical workloads and you want them to run, let's say, in minutes or seconds, then yes, that's a perfect fit for Ignite. If you just have, let's say, workloads and your SLAs are still in hours or days, then probably you can stay with Hadoop, right? Unless, let's say, you have 24 hours kind of operation in Hadoop and you'd like to reduce it to 1 hour or 2 hours, right? That's also possible. General kind of recommendation when it comes to seconds or minutes, think about Ignite because that's something that it can solve for you. All right, so that's the most straightforward and the simplest use case and the most straightforward pattern which we apply for some of our customers who like to flow Hadoop. But at the same time, there is another, little bit more advanced configuration when a customer, again, has Hadoop and Ignite separated from each other. They preloaded data from Hadoop initially to Ignite, but now, after both storages are up and running, they'd like to keep them in sync because what customers are doing, they have a copy of a specific subset both in Hadoop and Ignite. And by some reason, they just would like, to ensure that at least asynchronously, if anything is being changed in Ignite, in that data set, all of those changes have to be replicated to Hadoop. And the same requirement can be driven from the other direction. If, for instance, something is being changed in Hadoop, I'd like to see those changes eventually in Ignite. And for this situation, right, we are just doing one extra configuration. So we need to decide how would we replicate those changes. And when we're talking about the replication from Hadoop side to Ignite, there are several aspects. So there are several ways how our customers do this. First of all, if you're using MapReduce, you can just use your MapReduce special calculations that would, let's say, connect to Ignite, and they would send changes to both your Hadoop storage and to Ignite. You might want to use, you can also use probably Spark for that. Or also there is a special tool called Apache Scoop, which is used as a change data capture tool for Hadoop and any other technology that is connected to Hadoop on the other side of the wire. So that's like some of the basic tools which we see are being used for replication from Hadoop to Ignite. On the other hand, right, if you're like changing your data on Ignite side and you'd like to see those changes eventually in Hadoop, you can use, first of all, you can use some existing technologies like third-party technologies like Kafka or even Spark can be used, but for that use case you have to change your application code so that your application will be responsible for data synchronization. So meaning that if you write to Ignite, then also your application using Kafka or Spark has to transfer the same changes to Hadoop. But also there is another way around here when in Ignite we have so-called cache store interface, which is used, which can be used, like we can create, it's possible to create a special implementation which will transfer the changes from Ignite to Hadoop automatically for you. So, for instance, we have implementations for this interface for relational databases, for Cassandra, for Mongo, and basically what they do is that those implementations allow you to accelerate, let's say, your existing relational databases deployments. You just deploy Ignite, you are telling Ignite, all right, so here is my relational database, whenever anything changes in Ignite, please write through those changes to my underlying database. And the same concept can be applied to Hadoop. So the same. There is a special integration, and whenever anything is being changed in Ignite, it will be eventually written through back to Hadoop, so that you will see those changes. In your application code, your application developers will not be responsible for that data synchronization. Ignite will become the guy who is in charge of this. And here is like, I usually call this so-called gentle Hadoop acceleration, because for the first use case, usually when customers take and move a subset of the data from Hadoop to Ignite, they usually remove that subset from Hadoop entirely, and they require all of their kind of users of the application to use Ignite after that. In this use case, as long as you store a copy of the same subset both in Ignite and Hadoop, you can continue using some of the operations on Hadoop side, which take this data set, and also you are performing much faster with Ignite, right, for some of your new operations, for some of the logic which requires faster response time. And the final use case, which is the most advanced, and I wouldn't say that we have a lot of deployments of this use case right now, but at least to my knowledge we have 2 or 3 deployments, and probably the demand would grow, is when Ignite and Hadoop are again separated. They store the data sets, data specific for those storages, and for instance, customer even doesn't want to move anything out from Hadoop to Ignite. But sometimes what's needed is to join data sets which are stored both in Ignite and Hadoop. And that's the most tricky situation. We don't have any kind of out-of-the-box solution in Ignite for that, but there is a third-party integration called Arena Data in GreenPlan. By the way, does anybody know GreenPlan? All right, yeah. Yes, so actually, let me just tell you a little bit about this integration, how this integration works. So at the bottom of this picture, nothing changed, right? But what's changed is that the customer had, let's say, Hadoop deployment, then the customer deployed Ignite for some of the use cases, and now the story is the following: that, guys, I don't want to move any analytical data sets to Ignite, but sometimes I want to merge and join my operational data with my analytical data. How do I do this? And GreenPlan with Arena Data gives you this capability. So technically what happens, GreenPlan is a cluster of Postgres databases. And it stores special metadata and information about the data distribution both in Ignite and Hadoop. So basically, GridGain and Arena Data is aware of data partitions. So all the data that is stored in Hadoop and Ignite is split into shards or partitions, right? And for instance, GridGain knows, let's say, that partitions from A to D are located in Ignite, and partitions from F to X are located in Hadoop. And then, when you'd like to execute a select query, which needs to join data from Hadoop and Ignite, GridGain and Arena Data, GridGain-based solution of Arena Data will analyze this query. It will extract information about the partitions, so it will know, all right, for this data I need to go to Ignite, for that data I need to go to Hadoop. After that, each database, each storage will execute its part of the query, and Arena Data will do a final merge. So that's like from the high-level point of view. So we talked to the Arena Data guys, and they are saying that joins are supported, and like even there are certain optimizations when you, for instance, when you are not kind of happy about the performance of those push-down queries, then there is a possibility even to store some subset in GridGain and Arena Data, and that's also how you can accelerate your deployment. But what's also good about this solution is that when we were talking to the guys and asking, guys, how do you handle updates? And they will say, no, we don't want to deal with updates. So updates are on your side, because let your applications designed for Ignite and Hadoop update the data sets. We don't need to know about that. We just can kind of intelligently find out kind of all the information and keep it as metadata, and then just send all these selects to us, and we will sort out and do the rest of the job for you. So updates are not for us. We can possibly do them for you, but most likely you don't even need this in your production deployments. So overall, those were three kind of primary use cases which we are coming across right now with Apache Ignite, and so you might want to keep them in mind, so and use as a reference for your possible solutions whenever you need to accelerate Hadoop. And basically, if to conclude here, Ignite is not a silver bullet, right? Especially for Hadoop deployments. Whenever you just having any issues with Hadoop performance, think specifically what exactly you'd like to do with Hadoop, right? Or what exactly you'd like to accelerate. And if your goal, let's say, is to get to minutes or seconds SLAs instead of hours or days, then Ignite is a perfect fit for you. That's actually what's going on with hybrid transactional and analytical workloads nowadays. If you're still kind of thinking about hours and days, then probably you need to think about something different, because your investment might not prove your outcomes. So that's all. Thanks. Any questions? Yeah, please.
So what is the state of integration with Spark in terms of pushing down the predicates to
Ignite? So I think that the integration is done, so we can take those predicates and execute in place on Ignite, how we call it, like for most of the predicates and for most of the even SQL queries, right? We have an integration with data frames, even. We are trying to execute most of the operations on Ignite side, so that we don't need to move data from Ignite to Spark. So our goal is to kind of move a final result set, or like only those data sets for which we cannot execute those operations on Ignite side. So I think that we are done, unless like you test Ignite, you try it out, and you find out that some of the predicates are not executed in such a way, then community can have a look at this.
Thank you.
You're welcome. All right. Yeah, please.
When it comes to the question of making Hadoop more interactive, there's certainly more than one road leading to Rome. So in your recent experience, did you have a chance to compare Ignite with some alternative approaches? For example, Impala, Presto, or Druid, Hive LLAP. So those are all tools designed to make Hadoop more interactive, actually pushing Hadoop from the hours and days range into the minutes or second range. Did you get a chance to compare to see why people choose Ignite over the other tools?
Because here is I can answer, by referring to one of our kind of customers. Right now they're using Hive and they're using Impala. So they're just using those tools on top of Hadoop, right? Data sets. And they're not satisfied with them. And that's why they came to Ignite and they just would like to use us. But to use us for those deployments, they have to take data from Hadoop and to move it to Ignite. And after that they start using our SQL queries. The only reason is that like when you use, let's say, Hive, right? Hive is, as I remember, even if you run Hive SQL queries, well, not Hive, how it's called?
Impala?
Yeah, probably Impala. So there is like some of the SQL engine design for Hadoop, which is still based on MapReduce. But MapReduce is extremely slow. Probably that's not Impala, but there is another.
Impala is not dependent on MapReduce.
Yeah, there is another one.
Okay.
I don't remember the name. So, and like, that was the big deal. And when they just took and migrated data to Ignite, they just leveraged from our SQL engine, which is integrated with the rest of their memory layer. So you can set up indexes, you can allocate the data, you can, the way you like, and that's what they do. But we are not replacing, as I explained, Hadoop completely, right? They did this for some of the operations for which they need, let's say, to have minutes or seconds SLAs. For the rest of the data, they keep using Impala or they keep using Hive. That's what we see. And like when we are talking about Druid or when we are talking Impala, that's pure analytical use case. We are not coming after pure analytical workloads with Ignite. We are doing kind of transactional workloads kind of really well and kind of real-time analytics. So something like HTAP, what we call HTAP, when you need transactions and you need real-time analytics. But for advanced complex analytics, I would keep using Impala, Hadoop, and all of those guys, and Druid.
Thank you. So how Ignite plays in the cloud?
So we just support cloud. So we you can deploy us if you have
like EC2, Docker, or like
Kubernetes.
So you can.
Yeah, no any limitations. So and even like GridGain as a vendor, we released Ignite as a managed service. So if you'd like to deploy Ignite in the cloud and you'd like, let's see, our engineers to maintain it for you, you can do this with us. All right, thanks a lot for your time and for your attention, and I'll hand over the mic to the next speaker. Thanks.
All right, next up is Doug. Next up is Doug Hood from Oracle, and he's got a special guest speaker as well. For people who came in late, I'm Tom Dieterich, one of the organizers of the Bay Area Memory Computing Meetup. My colleague Tatiana is in the back there. She's the other organizer. And thank you for coming. Grab some food and some beverages. We got a raffle tonight. They make great re-gifting presents if you want to re-gift it this holiday season. There's an Apple Watch 3. There's Amazon Fire 8 HD. And then there's a Sega Genesis Classic console, which has 81 built-in games and has a cartridge, so you find some old games on YouTube, or not YouTube, eBay. You can plug those in. And so thanks again for coming. And
You can put it like down a little bit, like right there.
Yeah, I thought you can start.
Okay.
So,
all right, take it away, Doug.
So thanks, Dennis, for talking about analytics. How you can do that with Apache Ignite. I'm going to also be talking about analytics, but using different technology. I work for this company, Oracle. We do database stuff. We do transactional stuff. We do analytics stuff. So just hands up, how many of you do currently or have in the past used Oracle for database processing? Okay. Excellent. So, and how many of you have heard me talking before about Oracle TimesTen? Okay. So what I normally talk about is Oracle TimesTen, which is an in-memory database for transactional processing. It is the fastest OLTP database. I'm not going to be talking about that today. My job has changed. Not only do I work on TimesTen, I also work on Oracle in memory, which is for doing analytic streaming processing in the Oracle database, and also NoSQL. So without further ado, I'm going to hand over to my colleague Andy, who's a specialist on Oracle in memory, who's going to give you an overview of that technology.
Thanks, Doug. Whoa, that's pretty loud. Okay. Yeah, my name is Andy Rivenes. I'm a product manager with Oracle for database and memory. So database and memory is an option to Oracle database. It's all focused about analytics. We'll skip over the safe harbor statement. And so as Doug said, we actually have two in-memory databases. TimesTen, which is actually an in-memory database, and we have database in memory, which is analytics in memory, but it's still Oracle database, or part of Oracle database. So TimesTen, very fast, high-speed transaction processing in memory, as Doug alluded to, whereas database in memory is part of Oracle database and is focused solely on analytic processing. So Oracle database has traditionally been a row-based database, great for transactions. Column attributes are all part of a single row. It's kept in memory. It's very good for transaction processing. Rows aren't so great for analytics. It takes, you have to, especially in Oracle database, you have to look through a lot of data to do analytic processing. Typically, you need a lot of reporting indexes to make the analytic queries run reasonably fast. And it's quite a bit of overhead to do analytics with it. Those reporting indexes, we'll talk a little bit about, also generate quite a bit of overhead for doing DML, inserts, updates, and deletes. Columnar formatted database is great for analytics. You only have to look at the columns you're interested in. Typically, they're compressed. Typically, you can do vector processing on them. So very, very fast. For transaction processing, not so much, because basically that data is now stored in columnar format. You now have to stitch those columns back together into some kind of a row format in order to actually operate on it, because you have to be able to have the each of the columns associated with the other columns that they belong to, and essentially in the original row.
So just while Andy's doing transition there, if you have questions, please interrupt the talk.
Oh yeah.
There's a lot of information going to be doing. You've gotten the question by the end, so just interrupt. Having that dialogue is the interesting part.
Yeah, it's funny because database in memory typically, conceptually, it's very simple, but there's a lot of details. I'm not going to get through all of this. Our plan was to kind of give you a brief description of what database in memory is, how some customers are making use of it, and then a really short demo to kind of show you that typically what people will ask me is, well, if I just cached all of the row-based data that I've got, wouldn't it be just as fast as database in memory? Because isn't it just caching data in memory? And the answer is it's orders of magnitude different, and the reason isn't because it's in memory so much as it's in columnar format. So I tend to tell people that we could have called this the columnar database option or the analytics database option. And I usually say to people that in memory is really an enabler. It has to be in memory to make it fast, but it's the columnar format and the technology we use with the columnar format that makes queries orders of magnitude faster. And so let's kind of move on. So one of the big differences with Oracle database and the implementation of database in memory is we didn't change any of the on-disk row-based formats. That all still exists. It's not a full in-memory database in the sense that you can actually do an alter table, and you get to pick and choose the objects you want to populate in columnar format in memory. So it's not the entire database. You don't have to have, if you have terabytes of database, you don't have to have terabytes of memory to populate that data. The magic with this is the cost-based optimizer. So you don't have to change any of your SQL queries, any of your applications. The cost-based optimizer decides, does it make sense to access that data from the row store? Maybe you're doing insert updates and deletes. DML always occurs in the row store. Or maybe you're just doing small lookups, and so you only want to access an index because it's like least cost. But if you have an analytic query where you're going to sift through a lot of data, I typically say to people, analytic query basically is using aggregation to look for patterns or trends in the data. So when you're looking for a lot of data, cost-based optimizers can say, oh, it's much faster for us to access that data in columnar format. You see it in the execution plan. If you're familiar with Oracle at all, you can display execution plans, table access in memory full, and it'll be much, much faster. I typically tell people you can expect at least a 10x performance improvement. Very often people will see a 100x performance improvement. It is pretty phenomenal, the speed that can be achieved with this columnar formatting, the ability to skip over data that we don't need to look at, and to return that when we're doing analytic queries. Naturally, people, especially DBA types, will say, well, okay, that's great, but what's the cost of keeping this data in sync? Because we're preserving the Oracle transaction processing mechanism. You never see out of stale data. It's always a reconsistent view of all data. None of that changes within Oracle. And so naturally people say, well, conceptually, how do I keep that? Keeping that up in sync has got to be quite a bit of overhead. Since column store is pure in memory, we don't have any recoverability, any persistence with it. If the instance were to go down, the column store, it's poof, it's gone. So we have to repopulate when we start up. That's the in-memory part of this. And so keeping that data in sync is very, very low latency. Think of it as keeping an index up to date, yet you don't have any on-disk persistence, you don't have any undo or redo generations, because you don't care if the database goes down, it doesn't matter because that data is still in the row store. It's always in the row store, and then we're just allowing you to pick and choose particular objects to then populate in the column store. Any questions about that? Yeah.
So when you shut down the database and you set it up, how long does it take to put the column data into the memory?
So if the database is shut down or if it were to fail, how long does it take to then repopulate that data in the column store? And what we basically do is it takes, depending on your objects, it takes time to read the data off of disk, format it into columnar format, compress it, and populate in the column store. And you can actually, it's parallelizable in the sense that there can be multiple background workers which you can choose. It wouldn't be Oracle if we didn't give you a lot of choices. So you can actually specify how many worker processes you want to populate it. It's actually surprisingly quick, but it still takes time. It's still computer science. There's nothing's for free. And so it does take time to populate it. But once an object's populated, it stays populated. It's not a cache. So it's a one-time at instant startup, or you could actually reconfigure. So you might say, well, for daytime online processing, I'm going to have this set of data in the column store. At night, I'm going to have batch processing. I want this type of data. And so it's an alter table, no in memory, alter table in memory. You get that flexibility to choose. There is an option available to actually checkpoint the column store so that we can actually save it on disk periodically in the format, in the columnar format that it is in memory. So that can actually speed up restarts. But you got to get it into memory one way or the other. And with the row store, typically it's individual blocks of data that get populated into the buffer cache. So you're not typically doing the whole object, so you don't really tend to notice that warm-up period that happens when you restart a database and you're accessing just individual blocks for row access. Whereas with the columnar access, we're saying we're going to populate the entire object in the column store.
If I could just add to that.
Go ahead.
What we've got here is a database, and so you've got a table. That data in that table can be represented or accessed two different ways. As rows for transactional or as columns for vector processing. If you reboot the box, it takes time to load the data back into the column store. The point is it doesn't matter. You just type in SQL and the cost-based optimizer figures out, should I answer that by the rows or the columns or some combination. If you're doing analytics processing, it's faster to do it with the analytics. The point being, the query, if the column store is not available, will satisfy the result set from the row store. So it doesn't matter. You're still going to get the answer back. If it's all in the column store, it will tend to give you the answer back faster. So the time it takes to populate that column store with respect to recovery doesn't matter with respect to you doing queries and getting answers back.
Well, that's a good point. What he basically said was it doesn't matter if the data isn't populated in the column store. Actually, it does matter a little bit. So if a query, say you didn't have enough memory to populate all the objects you did an alter table on, the data so queries will still run. So if we'll get all the data we can from the column store, and any data that hasn't been populated yet, maybe doesn't fit because you didn't allocate enough column store, we'll get that from the row store. The only caveat is, obviously it's not going to be as fast if we're accessing the data from the row store as if we got all of it from the column store. So that's the only part where it kind of does matter in the sense that the idea is to populate all of the object in the column store to get the maximum speed throughput of scanning the data. And obviously we support parallelism, actually two levels of parallelism. Parallel query, which has been around in Oracle for a very long time. Then we also parallelize in database and memory scans, something we call in-memory dynamic scans as well. So, because basically at this point, when we're populating the column store, it's CPU and memory access. There's no disk I/O, there's no reason, since we're not doing DML on that data, there's no reason for us to lock any of the data. So it's literally just gated on CPU speed and scanning of memory in the column store. So the way you speed that up is parallelize. Yeah.
So if I have a transaction that's updating 1,000 rows, and on the column that's in memory, so I assume that the commit will only come back if and only if both the row store and the column store are updated with the latest information, right? When both sides are satisfied with my updates, then actually the transaction will commit, right?
No. So the question was, if I had 1,000 rows, or updating 1,000 rows, when I do a commit, do I have to wait for the column store and the row store to be in sync? And the answer is no. So what happens is, if I do an update of 1 or a bazillion rows, doesn't really matter, that process will take place as it always has, whether database and memory exists or not. So we're going to generate, we're going to make the change in the table, we're going to generate undo and redo for that change. We're going to update any indexes that are on that table and affected by that data. And we're going to basically update metadata in the column store. So it's literally just metadata in memory. And then we're going to commit. The actual data in the column store, or the columns that were changed, won't be reflected as actually changed until we, in the background, repopulate that data. So then you say, well, what happens then? So this is the second question for database administrators, is that, well, so then won't the queries be slower? Well, they'll be slightly slower, but in practice, you basically don't see the difference, because we're going to go to the row store to pick up those individual columns that have changed that we need to access, but all the rest of the data we'll get from the column store. The DML or insert update, the transaction processing will still take place. Actually, we have a video out on YouTube on the Oracle database of memory and the Oracle.com database of memory, and our blog that the Real World Performance team did on a transaction processing system. And what we did is basically we had a normal commercial transaction processing workload, and then we modeled that with database and memory reporting on top of that. We found that as long as there was enough CPU headroom to support the database and memory queries, that it didn't affect OLTP performance. And so this was on a highly concurrent system. So if you're interested in that, you can actually go take a look at the video. We kind of describe how we conducted we captured the workload and then how it worked, and you can actually see some graphs that go talk about where the performance was with database and memory and with OLTP workload. The only time where we degrade is when we run out of CPU headroom. Because again, you have to have CPU to process transaction processing, and then obviously you have to have CPU because all we're doing is accessing CPU and memory for the analytic workload. Does that answer your question?
Yes.
Okay.
But I have a
You may or may not believe me, but you can go out and look at it, or you can try it yourself. So.
I believe you, but here's the follow-up question, right? So the commit basically updates the row store side, right?
Mhm.
And the column store side only has the meta store updates.
Yes.
So for a period of time, no matter how brief, actually the actual data in the row store and in the column store are slightly different, right?
Yes.
The column store has the old version of the values.
Yes.
So what if the next select statement comes in a split of second, and that query is directed to the column store by the optimizer, so that select will read the dirty records
No, it won't.
because
that's the Oracle transaction processing. We have SCNs where we keep track of all of the system change numbers, and so we'll know that that data has changed, and we'll see it in the metadata, and we'll go back and pick up that change data that hasn't been repopulated in the column store yet from the row store. So you'll always see transactionally consistent data no matter what, and that's true in the row store as well as it is in the column store. And so basically what we'll do is we'll pick up the changed columns, because we know they changed, and we'll pick them up from the row store in the proper SCN sequence.
So is what you're saying there, Andy, we do a query, we've got updated data in the row store, the column store is slightly stale, and you're saying, if you query the column store, won't you see the old values? The point is you don't. The result set doesn't have to come from one or the other, it can come from both.
Right.
The up-to-date values in the column store will be shown. The old ones, we're going to go to the column store, pick them up, and stitch together the result. So it's a great question. It's a common question.
It's reconsistency. It's Oracle's transaction processing, and that's preserved across the column store as well as the row store.
Yeah, got it. Thanks.
Sure, no problem.
So Andy, we've got a bit over time. So
Already?
Yeah. Wow. Keep going.
We just got started. Any other questions? I actually like the questions better, but any other questions? No? Okay. So how easy is it to get started? You don't have to change any application SQL. That's huge for our customers. Nobody wants to go change SAP applications or e-business suite applications, PeopleSoft, custom applications. And is it better if I stand over here? And the reason is it's a cost-based decision. So the optimizer, good or bad in Oracle, the optimizer basically will parse the query, and it'll understand that which objects are populated in the column store. It'll have statistics for the row store. That doesn't change at all. And it's basically just going to make a cost-based decision. Do I access that data from the column store or the row store? So you don't say select from the row store, select from the column store. You don't have to know that. The application just says select from that table, and based on cost, based on the number of rows we're going to access, based on how many blocks or IMCUs we think we're going to have to access, the cost decision is, does it make sense to go after the data in the column store, table access in memory full? Does it make sense to go after an index access in the row store? Typically that's kind of, because if it's going to be table access full in the row store, we're definitely going to the column store.
So if I can just add to that, usually you have a row store, which is good for transactions, not so good for analytics, or you have a column store, which is good for analytics and not transactions. Because you've got a dual format, you can do both transactions and analytics at the same time, and the cost-based optimizer can figure out which is the fastest one. So it's not an either and or, it's the best of both.
So the use cases, the use cases primarily in the analytics area?
Yes. It's not primarily, that is the use case.
Oh, that is the...
That is, so we're not going to speed up inserts, updates, and deletes. That does not target. Now, I'll qualify that. See, it says later drop analytic indexes to speed up OLTP. The only advantage is, if you think about how database in-memory in a columnar format works, essentially you think of it as every column is indexed, if you will, because we're going to do table access in memory full, we're going to access just the columns we need to access, they're compressed, we're going to do all this stuff that I'm not going to probably get to talk about, SIMD vector processing, all this fancy technology, and I'm going to lose my train of thought. And so those analytic indexes that you needed in the past on row-based data are relatively expensive to keep up to date. When you do, like I said, when you do an insert or an update, we have to update all of those indexes. This isn't just us, it's everybody. And if you can drop most of those indexes, Larry said when we first brought this out that, oh, you can drop all your indexes. Well, you're not dropping primary key, foreign key, any referential integrity indexes, and you're not typically dropping indexes where you're doing small range scans, like lookups. But all those indexes you needed to add to get or your reporting to run, those you can get rid of. And that can save, typically, especially mature applications will typically have as much data in indexes as they will in tables. Keeping that up to date is expensive. Generating the undo and redo so it's recoverable is expensive. And so if you can get rid of that, it can actually free up considerable amount of workload in mixed workload environments to then actually give you headroom to run your analytics directly on your transaction processing data, as opposed to having to ETL it over to a data warehouse, create an operational data store, what have you, to actually access that data. You can do it truly in real time, which is what that video actually shows and that I mentioned. So we're going to run out of time. So the only other thing I'll take away here, I wanted to say, to actually set this up, you don't actually install anything separate. Oracle database comes with all of this fully built in. In-memory underscore size is a parameter that you just allocate memory in the SGA for the column store, and then you just say alter table in memory, alter partition in memory, alter materialized view in memory, and that's it. In the background, we'll populate that data, the database will open, everything will work, we'll populate that data. If the data isn't populated and you query data and the optimizer wants to access it in memory, if any of it is populated, we'll access it. Otherwise, we'll go to the row store. Your queries will never fail, and you don't have to change it. So that's the elevator pitch. I'm going to skip forward. I'm not going to talk about all this other stuff, why it makes it faster and what the optimizer does. And I just kind of want to mention some of the customers, some of the use cases. Yes, sorry.
Are the slides on Meetup, or will the slides be available at Meetup?
Sure. I don't think they're currently there, but we'll definitely, we're willing to put them out there.
Yeah, we can post it to the site if you upload them and share the link. And
sure.
And then this is also being live streamed on YouTube.
Oh, okay. Cool.
Great.
So, go ahead. Is that good?
No, I was just going to say they'll let you flip through things really fast.
No, I know. I'm going to skip over it because otherwise we're going to run out of time, and I wanted to catch a couple use cases and then a really short demo, and then you're going to kick me out of here. So. Basically, if you look at this, I have two pages of customers. All these stories are in detail on oracle.com for database and memory if you want to go back and read how people are using this. But the bottom line is data warehousing, BI, mixed workload. Those are the use cases. Anywhere you're doing analytics, when you're doing significant reporting, typically if you're doing sub-second queries, database and memory could help, especially for avoiding any I/O, but realistically, that's not typically what people are worried about. You're worried about reports and queries that have taken a long time to run. You want them to go faster. And so AT&T Wi-Fi, one of our first customers with database and memory, business objects. Villery and Bach, SAP, a lot of SAP customers. Germany is a big market for us, and then US as well, but SAP is really big in Germany. Demobular got rid of Netezza, basically migrated all of their IT infrastructure into Oracle database, used database and memory to free up a considerable amount of capacity. Bosch actually, justified their use of database and memory strictly by, I mean, obviously the analytics were faster, but the dropping of their analytic reporting indexes justified the investment in database and memory, which is kind of cool because we always say, well, yeah, if you drop all your analytic reporting indexes, all this great stuff's going to happen. But here's a case where we can show that it really did in a real world use case. Because you're under the Oracle guys, so you're not necessarily going to believe me. Hopefully you'll believe our customers. And then other, Mankind Pharma, again, mixed workload, Shanghai Customs, mixed workload, Lufthansa, reporting application, Lion, SAP ERP. ERP and e-business suite are, by the normal nature, aren't super friendly to analytics because they're very well structured, very well indexed. But any kind of custom reporting you're doing on those kind of applications can definitely benefit from database and memory. The standard reports typically run pretty well and are very well tuned. I mean, e-business suite's been around for a really long time. And so it's pretty well tuned to that. There are some white papers that describe how to make use of database and memory with the different applications. And again, all of that's available on the website. with Oracle.com, and I have it at the last slide, in our blog, and we do a lot of technical articles on database and memory aspects as well. It's not fluff, because I'm not in sales, so I'm actually a product manager. We're in Oracle, product managers are technical and essentially think of them as tech consultant type people, as opposed to having much to do with sales. At least that's what I would like to look at it. So I did want to do the demo. So what do I got to do? Escape and have it somewhere here. Can you help me out?
Okay, this is a funny thing. I use Windows, Andy use Apple, and they're different. So I'm going to do something really technical here. I did an Alt.
I never use those.
I did an Alt Tab. That's how you get between windows. And I'll press play.
Even when I use Windows, I didn't do that. So all this is a video of what we did at Open World, and it basically uses German Weather Service data from Germany, and that's why you kind of see the European map. I'm probably in the way again. And what we're doing is we're just clicking on a region, in this case Paris, and spring, and showing you the average temperatures. All that's great, but the takeaway here is, and this is also, there's a video that describes all this on YouTube as well. But if you've noticed that the column store is screaming fast compared to the row store. This is on Exadata, two separate Exadata nodes, one running the column store, one running the row store, and with tons of CPU and all the magic that Exadata has, and database and memory is still screaming fast. So hopefully that's a tease. You know, the cool thing is you guys can actually either Oracle Database XE18C just came out, or you can download a Developer Days VirtualBox, and it's there. You can run this on your laptop if you want and experiment with this. You don't have to have some big server to give this a try. You don't have to have Exadata. Anywhere where Oracle Database runs, 12C, 1202, 12.2, 18C, database and memory runs, you can try it out. Don't do it on your production systems because maybe the license guys might get mad at you, but if you do it on any of the developer distributed stuff, you can try this out to your heart's content.
Yeah, so if I can just add to that, the whole point is you're doing the same query two different ways. With the column store, you can literally process billions of rows per second. That's the point. With the row store, it's pretty fast, but it takes longer. Per core.
Per core. I mean, it's phenomenal.
It's crazy. And
well, here's one from the start. We just picked a region, but again, look, it's already done. So that's kind of.
So I think we should just stop at that.
Okay. We're going to go over.
Yeah.
All right.
So any questions?
Yeah. Any other questions? That was like the 50,000 foot level of database and memory. We have lots of information available. If you're interested, my email address is here. Believe me, you can email me. I'd be more than happy to answer your questions. We'll put the slides up on the Meetup, make them available. If you can't remember anything else, just Google for database and memory or Oracle database and memory. We're all over the place with the blog and then some of the Oracle.com stuff. But lots of interesting technology if you're into, want to explore that a little bit further. Thank you very much for letting me talk to you for a few minutes tonight. And Debbie, thanks.
Thanks, Doug. Okay. Next up is John Lockwood.
Okay.
Hey, John.
Hey,
how are you?
Good.
Great job. All right, John is the CEO of Algo-Logic Systems, Inc. And once you get mic'd up, you can explain a little bit about your company, John.
Yep.
And John's talk is in-memory key value store for Fpga for ultra-low latency and high throughput. I don't know what that means, but John's going to explain it. So,
I need a plug for the projector.
oh, you should have a.
It's on the floor there, I think.
I'll get it. Oh, that one. Yeah. Did you need a dongle, or you got it in there?
Nah, good.
Okay. Come up with a secretary here. We have plenty of beverages, soft drinks, wine, and beer in the back if you're thirsty. So. And we got some more. There's some more food left too. If you guys want seconds. All right.
Okay, so tonight I want to talk about transitions. Okay, so I'm John Lockwood. Run a company called Algo-Logic, which is algorithms and logic. And tonight I want to talk about in-memory computing with an Fpga key value store. And so first of all, Fpga is that, so we work on something we call gateware. Gateware are things that run in logic gates instead of running in software. And so gateware is a lot like software in the sense that we write code, we write Verilog typically. Some people write VHDL. But this compiles into parallel logic gates. And so instead of compiling to assembly code that runs on, executes sequentially on a microprocessor, on an Fpga it compiles into lookup tables. And so these lookup tables, as you can see, this is a chip layout of what appears inside the Fpga when you synthesize a chip, is that it's a bunch of logic gates that are communicating, parallel state machines that are communicating with each other. And so logic tends to cluster when you route and place it, so they come together. And so these get placed and routed into the Fpga device. And so, again, CAD tools take care of doing that, and FPGA people don't build chips. And so Algo-Logic does not make hardware. We write software, or we call it gateware, and it's apps that run on FPGAs. And we apply this to doing data center networks. And so in the data center, of course, there's volumes of traffic, and most of that traffic is carried over Ethernet. And so there's problems about searching through streams of data and also supporting cloud services. And so, for example, the Microsoft Azure Data Center, every time you use Office 365, all of your traffic, every byte of network traffic is passing through an FPGA on its way into the Microsoft Azure Data Center. And so there's an FPGA in every single node of the Azure Data Center at a ratio of 1 FPGA for every 2 sockets of Xeons. So there's millions of these FPGAs deployed in the Microsoft Data Center. And there's many FPGAs deployed, for example, on Amazon. The F1 instance, which is one of the node types on Amazon, contains a big FPGA device. And so people that do compute acceleration, like people that use GPUs, can use the GPU instance. People that use FPGAs can use the FPGA instance. So FPGAs are still kind of a niche technology. It's definitely an alternate type of heterogeneous compute, but it seems to be a space that's growing. And so when you use FPGAs for networking, there's a couple advantages that fall out. And so one of the things is that we're able to get down to really low latency networking times. And so our benchmark is sub-microsecond, so 1/1,000,000th of a second for doing network transactions. It can be very deterministic because it's a lot like a chip design in the fact that you design pipeline stages for all of your data processing. And so there's no uncertainty about cache lines or cache misses. There's no operating system. There's no embedded scheduler. Everything is explicitly scheduled when you design the hardware. And so you can get really high throughput for networking systems. And so Cisco typically prototypes a lot of their ASICs with FPGAs first. Some applications remain in FPGAs because you can get a lot of throughput through them. But you can still go back and change it. And so unlike an ASIC, if you make a mistake, is that you can just reflash the SRAM. It's all in memory, actually. Is that the FPGA configuration is in-memory configuration that controls the logic. So you just reset the chip, put a new bit file into it, and you have a whole new chip design that's running. And so taking this is that we primarily focus on putting IP cores together. And so things like offloading TCP stacks, protocol parsers. We do a lot of low latency trading for Wall Street. You do high frequency trading. Speed is of the essence. If you can be a little faster than somebody else, you have an edge. So we help people get that edge. So primarily what Algo-Logic does is we build these IP cores, which are RTL circuits that run in logic. And then we put those into FPGAs. We route and place those into Xilinx, or the company Altera that was acquired by Intel a couple years ago, are the two big manufacturers of FPGAs. Those companies in turn put those chips, or board companies put FPGAs onto typically PCI Express form factor boards. So boards that are the same size as they range in size from small NIC, like a half height, half length PCI Express card, to the bigger ones now, which are the same size as a GPU. So full height, full length, sometimes double width if you want a lot of space for cooling. And so then these FPGAs go into servers. And so this is a 1U server. And so and the 1U servers that we have, you can fit 2.5 cards in each machine. They also can go into scale-out systems. And so Intel, for example, released a server which is a 2-socket server, but what's unique about it is it has a Xeon and an FPGA in different sockets. And then more recently they integrated this two together, so the FPGA and the Xeon are actually on the same socket and communicate over QPI to each other. And then this is what Microsoft does as you scale it out, is that you put lots of these servers into racks, and then you provide network connectivity with a lot of bandwidth. So what I want to talk about today, though, is in-memory databases. And so an application we put together was this FPGA key value store. And so the concept here is having a regular PC host that has an FPGA card and allowing data in the key value store to be accessed both by the CPU and over the network directly. And so that you can do a network query over Ethernet and go straight into the FPGA, pull data out, or write data in. You can also have the CPU, if it's doing analytics, for example, can go to the FPGA, pull key value pairs out, and write them back in. And this is a very simple association. We're still in early stages of doing offload. And so primarily the functions that we support are the basic CRUD functions. So we can associate data with keys. You can read keys out. You can replace keys. You can delete keys. And you can insert keys. And so it's CRUD functionality. And so all of this is implemented entirely in FPGA logic. And some FPGAs have processors on them, so you can have an ARM CPU alongside that, or the Xeon. That's not what we're doing, is that this is actually straight up RTL logic. So there's the CPU reading data out and the FPGA reading data out from the network. And so you can also scale this out. And so since most data centers consist of having top-of-rack switches and then a number of nodes in the rack, and almost all data centers use Ethernet as the primary connectivity, either 10 gig or 25 gig, 40 gig, is that the model is that you have top-of-rack switch and then connectivity to each of the nodes by just cheap Ethernet. And so doing this, you can scale it out. So you can get data for widespread deployments in a data center, and you can still get really low latency because any read is just your Ethernet switch latency, which is really short, and then the latency of the FPGA to do the key value store. And so then the scale-out configuration is you just hash your data, so kind of do like a Hadoop scale-out. You distribute your data with hash algorithms so that your data can be distributed. If you want replication, you can also have multiple writes or use multicast to send data out so that it gets written into multiple cards so that you don't lose data. And then what you can do with this are applications like doing inference. And we found that inference is a great workload for these in-memory databases because the appetite for doing intelligence is very high right now. Is that everyone wants to build machines that can think, or machines, and our role in this is building machines that can think fast, or rather do inference fast. It's like you've already trained them, which is typically done with GPUs, so the FPGAs are good at doing the inference, which is making decisions with the data that you've learned. And so if you've got, for example, a self-driving car, it's really important that your self-driving car responds deterministically. Is that it's very important that you can bound how long it takes for it to process an image and to take an action. And that's a hard problem for a GPU because a lot of times the GPUs have very deep image pipelines. And so even though they have a lot of throughput, it can take them many, many frames before they can catch up and be processing the last thing that just came in. And if you saw the accident that happened with the Uber last year, there's at least a second before that pedestrian was killed. It was a woman walking her bicycle across the street. Now, granted that she was jaywalking, shouldn't have been there, and granted it was dark outside, she was wearing dark clothes. All that's true. Any human probably would have killed her because she stepped out in the street. But a computer shouldn't have. Is that there's at least a second, maybe a second and a half before the impact that she was visible to the cameras of the car. And it was all recorded, so you can play it back on YouTube and see what happened. Is that the problem was that image pipeline that Uber was using, and knows what written in software on the GPU or combination of software and GPUs, was so slow that it took over a second and a half because the car didn't do anything at first. And so it's shocking that this person was killed. Again, the computer shouldn't have let this happen. And we're concerned about things like this, which require real-time actions. And so having that real-time deterministic latency can be really important for real-time applications like self-driving cars. It's certainly important for trading. So the key value store that we're looking at is just these. Obviously, you guys do memory compute, so associating pretty much anything with anything for NoSQL databases. And so things like, for example, can be names with numbers, IP addresses with MAC addresses. For data dedupe, you can have content hashes, and so that you can have storage blocks. One of the applications we used our KVS for was a cache in front of a flash file system. So using in-memory, which in this case in SRAM and DRAM, which is about an order of magnitude faster than flash memory, which is about an order of magnitude or two faster than hard drives. The in-memory compute is the fastest tier of storage. And so if you want to do things like caching a flash file system, an in-memory compute system, or in-memory database is really useful. I mentioned the car locations, for example, with vehicles. You can have a latitude, longitude to keep track of the vehicles. And then other applications like graph search. If you're searching for vertices and edges, you need to traverse a graph. Especially if you have a generative case of a graph search where it goes into a linear search. And so it's node to node to node to node. Is that the read latency of the database is critical because the time it takes to traverse that graph is directly equal to the number of nodes that you have to read through. And so, so some of the other applications that this group and other people work on that we work on are things like using sensors. And so having sensors to keep track of movement, acceleration, social, some of the lower latency things. Facebook uses memcached extensively, or did, newer versions of that now, to keep track of the user status. And so, for example, one thing that's probably not a good FPGA application is like your marital status, is that it should be, you can be married, you can be single, it could be complicated. That probably doesn't change so fast that you need to put that into an in-memory database. The primary benefit of having it in a cache is the fact that you can have lots of users reading that without needing to take it back to the primary storage. Communication, cell companies use it for network handoff, databases for users payments, and for security, things like micro warrants are useful. And so anyway, getting back to the servers with these accelerated cards are really no different than most servers, is that they are typically a Xeon server with a PCI Express card populated with an FPGA card. And so we've worked with Xilinx that makes a number of very big UltraScale Plus FPGAs, as well with Intel, which was Altera, that was the other half of the market, or other large fraction of the market, that makes cards like this that fit into a half slot of the server. And so applications that implement the key value store run completely on the FPGA, and then the CPU talks to it over the PCI Express bus, and all the networks and sensor devices just talk to it over Ethernet. We did a benchmark of how fast a key value store runs when it runs kind of in what we call traditional software. So if you take a Linux server, you put a standard NIC into it, a 10 gigabit NIC, and you write a user space application in C, or in our case C++, compiled code, and you take network traffic in over the Ethernet by doing standard Berkeley style read, write, I/O operations, which is probably about 99% of things on the internet are still written in this model of sockets, is that that's this model of compute. We took the same application and used the kernel bypass approach. And so high-frequency traders have been using kernel bypass for years to avoid the operating system in their latency stack. Intel introduced DPDK as their acceleration stack, where you can accelerate the data plane by having processors that directly read data from the network card, put it in message queues, send it back. And so with the kernel bypasses, that you never touch an operating system, your entire application just runs as threads on different processor cores. And then the last mechanism is to put the entire application onto an FPGA. And so in this case, we're taking network traffic that comes right off the Ethernet, going into the FPGA device, doing the key value store function, using the memory that's on the FPGA, which is the fastest table, as well as all the memory that's around the FPGA, in this case DDR3, and then returning the result back over Ethernet without ever touching the PCI Express bus, without ever touching the processor, no software involved. And so we did a benchmark of how much different is it to do things like this key value store in-memory database on a Linux system versus going to kernel bypass and then taking it all the way to an FPGA. And so the first metric was throughput. And so we looked at the throughput, and this is a chart that shows the percentage of packets that are processed. And so this is just loading the machine up, starting from 0, and throwing more and more packets per second at it until the machine starts dropping packets. You can't take the workload. And so the software starts dropping first. This is a log scale down here. And so at about 4 million messages per second, we saturated our Linux i7 server, where at that point, any load beyond that was just lost packets. And so here we can see we start dropping about 4 million. DPDK, doing the kernel bypass, avoiding the overhead of going through sockets, making multiple copies in memory, straight up processor core, took us further. This took us out to 15 million key value store lookups per second. And so it's pretty good, that's an improvement. For the FPGA, because it's designed as a pipeline to take every packet in, and you've allocated enough internal resources to take the full data path, and you've got memory in parallel that's doing lookups, this took us out to 40 million messages a second, which was the full line rate of the 10 gig E. And so we've done this on 40 gig E, and it's at 40 gig E, the numbers are higher, which I'll show shortly. So the point is that you can do lossless databases at line rate with high-speed Ethernet by offloading to the FPGA. The most dramatic result was latency. So we looked at the latency distribution for running Linux on a host. And so this is, again, this is standard sockets, opening up a C++ program that talks to Linux kernel and does reads. Very simple database operation. It reads the request as a UDP packet, it parses the key value request, goes to the hash table to find that key value pair, pulls it out of memory, puts it back into a packet, and sends it out. So doing that in software came up with an average latency of about 41 microseconds. And so, but with a pretty decent sized tail, about 10 microsecond standard deviation, and actually in a long tail. And so when you have things like operating system events, you can end up having delays of well beyond 100 microseconds at times for a read request into the database. But on average, it was over 1 million samples, it was 41 microseconds. Big advantage to bypassing the operating system. So doing kernel bypass is about a factor of 10. You go from taking tens of microseconds down to a single digit micros, a few microseconds. And so this is what we've seen, in this case, getting it down to 6 microseconds to do the packet read, key value store lookup, putting the value back and sending it back over the network. With just a little bit of deviation. So a few operations are a little faster, a little bit slower, but mostly probably just due to cache hits and cache misses of the L1, L2 cache by the processor core. One more order of magnitude faster is what you can do with the FPGA. So going from about 6 microseconds to a half a microsecond, you're now doing requests that are 10 times faster than kernel bypass. And so this is, and you can also see that about half the packets were at 1 clock cycle, and the other half was 6 nanoseconds more than that. So the only randomness is at what phase of the clock cycle the packet hits the system at. But it's a very tight distribution. It's almost an impulse function in terms of the time deviation of the processing time is within 6 nanoseconds. And so, as you can see, going from having 41 microseconds of latency in Linux to 6 microseconds with kernel bypass to a half a microsecond with almost no jitter is a big gain. And for us, when we use this key value store for high frequency traders, this is what makes them profitable, is that trading 10 times faster than your neighbor makes a difference when you're on Wall Street. So in the data center is that we, again, for the latency, 88 times faster than Linux, 14 times faster than kernel bypass. The throughput, about 3 to 13 times faster for number of operations per second. There's also power savings. If you avoid moving data across load store operations and a microprocessor and hitting different cache lines, you can reduce power drastically. And so about a 10 to 20x reduction in power. So we have a white paper that spelled out all these results with all the metrics and machine configurations and all the settings that we use to get that. And so now, how do we deploy this? Where do we plan on using this? And so we see kind of the world full of internet devices, this world of IoT. It's been estimated that in, I think, the next 5 or 10 years, that we're going to have on the order of, on average, about 10 devices for every human. So right now, I think we're at about parity or so, where all of us, half the population at least, has a cell phone, and some of us have laptops and desktop computers and servers. But there's about the same number of computers as there are people. And in the future, that ratio will be about 10 to 1, where there's about 90 billion processing devices that are on the network compared to about 10 billion of us humans. So a lot of devices, a lot of traffic will be coming in. And so there's a lot of opportunities for this group that's building in-memory databases, because there's a lot of data to be collected and processed and analytics to be run, so that you can make real-time decisions with the data that's coming in. So that from the IoT data that's coming in from sensors to the time that you're deciding how to do a stock trade or how to drive your car, is that these machines need that data so they can learn, and so they can also make decisions. And so storing data in memory via SRAM if it needs to be super fast, or DRAM if you have a little bit more time, or in flash memory, NVMe if you've got a little bit more time than that, really is orders of magnitude faster than what we had without in-memory compute. And the appetite for this is being fed by machine learning and inference. And so we see all sorts of workloads that are coming in from GPUs, processors, network processors, and FPGAs that can load up the workload. The scale-out numbers are kind of ridiculous to talk about right now, but if you project what happens when you put a number of these machines into a rack, at 40 gigabits, with 40 gig Ethernet, is that we've been able to get 150 million read operations per second out of the SRAM in-memory database. That's per card, and so that's on a small little PCI Express card. And if you have 40 of those in a rack, that gets you to 1.6 terabits per second of 40 gig times 40. The latency at 40 gig comes in at 342 nanoseconds. It's 0.342 microseconds, micros. So it's still 1/3 of a microsecond is the latency. So some microsecond latency. And then for programming is that the key value store, although the key value store itself is kind of cryptic in the fact that it's RTL, but the software interface is just a standard open source software package. And so for doing simple operations like CRUD, to create keys, to read keys, to update keys, delete keys, is that there's just a C++ library, a Java library, Python has been done so that you can, standard libraries, so that any software process, as fast as it can send packets out over the network, can load up one or more of the key value stores that are on the network. So we see this opportunity to scale up these in-memory databases. The good news is for this group is that there's a lot of room to grow, is that we see these compute accelerators being able to get in-memory compute systems to get into these massive amounts of performance. And then they scale out in the same way that Hadoop and other types of scale-out systems work, where you can load, distribute traffic, and replicate traffic across the network. And so in this case, is that these are the results that we have so far, and we're still working on enhancing this. To fully implement the key value store in FPGA logic, to attach it directly to Ethernet so it's on the network, To use the fastest memory, to use QDR SRAM for the top tier of storage, DDR2, DDR3, HBM for the next tier, and then Flash for the third tier. And then making this available so it's got a fully open software API, where there's no restriction for kind of a BSD style license to use this. So that's it. That's who we are. That's what we've been up to. I'd be happy to talk to anybody here that's interested in FPGAs or just interested in has applications that need real-time performance to see if there's ways we can work together. Thanks. Questions? Yeah.
Oh, maybe a couple. So from a KBS perspective, to implement an LDL, you must have evaluated a bunch of KBS stores, such as from Berkeley DB to Redis to others. Else like comes to mind as well. They have an open source version. I'm curious if you can even just talk at a high level, just like what feature that you think are crucial and which one that you want to actually that you